To start off with today, I want to experiment with probability density functions, PDFs, for continuous random variables by making up a distribution on my very own, of my very own. You could do the same. You could make up a distribution of your very own. Whether it's got any applications or not is not really the question. The question is, can you come up with an example distribution based on a PDF, little f of x, that you would want to, as always, be non-negative, always greater than or equal to 0. And with continuous random variables, you'd want to integrate it to 1. But to give yourself maximum flexibility, you might want to allow unspecified parameters, like a c that you have to figure out, that came up on the exam, or maybe even a couple unspecified parameters. How about this kind of function? C divided by x to the p power, where by writing this, I'm implicitly kind of assuming c and p are both positive. Yes, I could also write this as c times x to the negative p power as well. C and P, I'm implicitly assuming, are both positive. I should specify the domain over which this formula is relevant, because in reality, it's really going to be a piecewise formula. It's going to equal this. Say if x is greater than or equal to 1, do I have to pick 1? No. I could pick 2. I could pick 3. I could pick 4.72 right there. I could pick pi. I would not want to pick 0, right? Because then I'd be dividing by 0 here when x is 0. So effectively, it's this when x is greater than or equal to 1 and 0 otherwise. OW means otherwise. And I don't have to worry about this function having a vertical asymptote at x equals 0 because I'm not approaching x equals 0, so it's no problem. But it is a domain over which, well, the interval over which this is positive is an infinite interval. It goes on forever. So if I'm to choose C and P, and that's my goal right now, is to choose C and P to make this a valid PDF, I'm going to have to do an improper integral. Oh, boy. Improper integrals, what are those? Like this. Integrate from 1 to infinity, for example. Can I integrate this from 1 to infinity and choose C and P so that I'm guaranteed to get 1? Doesn't seem like it's probably possible, does it? I mean, there's 2 unknowns, 2 parameters, C and P. How could you possibly choose both of them to make this equal 1 unless it's just lucky? Well, let's just see what happens. Technically speaking, this is a calculus 2 thing. Improper integrals like this, where there's an infinity in the upper limit of the integral, are limits of proper integrals. And so we want to be picky right now. We want to write this as a limit of proper integrals as the upper limit of integration, b, goes to infinity. I'm taking a limit as the upper limit of integration, b, goes to infinity. We're using the word limit in 2 ways there. Lim means taking a limit, but b is the upper limit of integration. 2 different meanings of the word limit there. It's the right endpoint of the interval of integration, but unspecified here. Make it an arbitrary b, but then in the end, let b go to infinity. Does this limit exist? Remember this kind of thing coming up in Calc 2? It's a question of, does this improper integral converge or diverge? And with integrals, you often just had to try to do the integral. With series, infinite sums, you also had a bunch of other stuff, tests. There was like the integral test, the ratio test, the root test, perhaps. You did the, what else? Comparison test. All sorts of tests. It's harder for series than it is for integrals. With the integrals, you just try to do them, if you can. Let's see, can I do this integral? Carry the limit sign along. Yeah, just use the fundamental theorem of calculus. C is a constant, so it stays as it is. I've got to add 1 to the exponent, negative p plus 1, and divide by that same number, right? Well, or is that correct? Or not? Is there a problem for any value of p here? If p is equal to 1, that's a problem, right? Because I'd be dividing by 0. So this is if p is not equal to 1. I can say that, because if p is 1, I'd be dividing by 0. If p is 1, I'd really get a natural log, actually, wouldn't I? I'd really be integrating c over x when p is 1. So we're pretending p is not 1. All right, continue. Let's see. The constant c can be pulled out in front. C times the limit as b goes to infinity. I mean, it's a little complicated looking. Maybe it's best to write it as b to the 1 minus p over 1 minus p minus 1 to the 1 minus p over 1 minus p, right? I'm plugging the numbers in. 1 to the 1 minus p is just 1. What can I do now? The answer is, it depends. What do you think it depends on? It depends on the value of p, whether this limit is going to exist or not. If 1 minus p, if that exponent of the b is positive, then b to the 1 minus p, b to a positive power, is going to go to infinity as b goes to infinity. This limit will not exist. It'll diverge to infinity. The only way this limit is possibly going to exist is if this power of b is negative, which means you could also write it as 1 over b to the p minus 1 power if you wanted to. The limit of this part right there exists only if 1 minus p is negative, which is equivalent to saying add p to both sides. 1 is less than p. Another way to say that is p is bigger than 1. There's another restriction on the value of p, and it's going to fail to exist if p is less than 1. This integral only converges when p is bigger than 1. So now I'm going to assume p is bigger than 1. Assume if p is bigger than 1, what is the limit going to be? C times, what is this limit going to be if p is bigger than 1? If p is bigger than 1, like 2 or 3, 1 minus p is negative. B to a negative power goes to 0 as b goes to infinity. This part goes to 0. And I guess this part's constant. And I guess this can simplify if I distribute the minus sign through the bottom there to c over p minus 1. Right? A little bit of algebra there. That limit is 0. This limit, that's a constant. Its limit is itself. Got a minus sign there. I distributed the minus sign through the bottom, which is fine. Running that c in there simplifies to that. What value of c and p can be chosen to make this equal to 1? Well, you can't solve that in general for both c and p. However, as if in linear algebra, you treat one of these like if it's a free variable, then you can solve for the other ones in terms of the first one. Setting this equal to a 1 is equivalent to saying c equals p minus 1, which is also equivalent to saying p equals c plus 1. If that condition is met, and if p is bigger than 1, so I guess c is bigger than 0. Well, I already assumed c was bigger than 0. Yeah, to do the calculation, I do have to assume p is bigger than 1, though. I didn't know ahead of time that this was going to be the relationship between p and c. That's got to be the relationship between p and c in order for the original function to be a valid PDF over the domain from 1 to infinity. So I can now go back to my original PDF and, for example, replace the C up there with P minus 1. So my new PDF, new and improved PDF, is f of x. Let's go ahead and write it in a piecewise way. Replace C with P minus 1. P minus 1 over x to the P. If x is bigger than or equal to 1, 0 otherwise. And I am assuming P is bigger than 1. That's a way to specify more precisely that this is going to be a PDF. And it'll be a valid PDF. Is it of any use? Well, that's hard to say. What is a possible use of this? Could you use this on the job? If you had a situation, a statistical situation where you gathered data, and in gathering data, this is just a little preview of statistics here, in gathering data and plotting that data with what you might call a dot plot, which effectively is a number line with a bunch of dots marking the values of x. If all those values of x happen to be all bigger than 1, and if they all happen to cluster pretty close to 1, typically speaking, but every once in a while having high outliers, relatively large values of x, maybe even very large, a function like this might be a pretty good model. Its graph would look about like that. And the fact that the PDF is higher when x is close to 1 is reflecting the fact that the data are denser close to 1. Probability density function. And where the PDF is lower in value is reflecting the fact that the data are less dense when x is large. Conceivably, for some value of P, that could be a pretty good model where integrating this gives you probabilities for the data being in certain ranges. I'll say that again. This is super significant. You want to apply statistics on the job in 10 years in really pretty sophisticated ways. Listen very carefully to what I'm saying. And then 10 years from now, come back and watch the video to remind yourself. Okay? You want to apply this kind of thing on the job, maybe. It might not be a good idea to apply it on the job, but maybe. Look for a situation where you've got data that's always greater than 1, typically clustering close to 1, very rarely having high outlier values, and finding a value of P that models the data in such a way that the probability of a data point being, say, between 2 and 4, the area under the PDF between 2 and 4 matches pretty closely the percentage of the data in that range. Of course, you got to do it for every range of intervals of numbers, not just 2 to 4, but also 2 to 5 and 2 to 6 and 2 to 7 and 3 to 15 and 17 to 100. It technically, to be a good model, has to be reasonably close probabilities for all those ranges. Oh, it doesn't sound so easy. Doesn't sound like maybe it's necessarily a good model. But that's what happens with mathematical and statistical modeling, is you hope you can get away with something simple, even if it's not completely accurate. You hope it's good enough. Okay? We should do more with this model, though. Yes, I could find probabilities now. Maybe I should go ahead and find that probability of P of x being between 2 and 4. I'd have to pick a value of P. Well, okay, maybe the answer depends on P. Let's go ahead and leave P unspecified. What is the probability of x being between 2 and 4? And with continuous random variables, again, it doesn't matter whether you write less than or equal to's or strict less thans. It doesn't matter if you make one of them a less than or equal to and the other one not. All these probabilities are the same if x is assumed to be continuous. Why? Because we say so. That's the way these continuous models work. The probability of x taking on any specific value, like 2 exactly, is so small, so tiny, that, well, you might as well call it 0. right? 2 exactly to infinite precision? I don't think so. Right? Imagine measuring the length of something and saying it's exactly 2 inches, no deviation from 2 inches at all, not likely to happen. You'd have to measure down to the subatomic level. All right. So effectively, the probability that x equals 2 exactly is 0. All these are found by integrating this function from 2 to 4. And yeah, let's go ahead and get the answer in terms of p. I could pick a specific value of p, but let's try it without doing this. Okay, well, c again is p minus 1. I'm doing the same kind of integral as before, really, except now I'm going from 2 to 4 instead of 1 to infinity. I'm going to get this, just like before, for my antiderivative. This is just a big 1 right there, right? So I really get 4 to the 1 minus p minus 2 to the 1 minus p, whatever that happens to be. If p is 2, for example, or yeah, if p is 2, this would be 4 to the negative 1 minus 2 to the negative 1. Oh, did I make a mistake? That's going to be a negative number. I don't want that. What's my mistake? Anybody see a mistake? Oh yeah, negative 1. Okay, that's negative 1. Thanks. So it's going to be 0.5 minus 0.25 is 0.25. Yeah, this is a negative 1. I was thinking about switching the 1 and the minus p around, and for some reason I thought it was the same as p minus 1. Brain freeze there. Okay. So if p were 2, this is going to equal 0.25. What else would we want to know from this model? How about the mean? How about the variance? How about the standard deviation? What's the mean? Mu, expected value of x. Whereas with discrete random variables, you have to add x times the PMF values. With continuous random variables, you have to integrate x times the PDF values. Overall values of x, which in the general case in the reading is written as an improper integral from minus infinity to infinity. But as is often the case in these models, it doesn't have to be done from minus infinity to infinity. This one can be done from 1 to infinity because, again, the PDF is assumed to be 0 when x is less than 1. So once again, using the general PDF formula here. And okay, let's be technical about it and write the improper integral as a limit. Like this. X divided by x to the p power is really the same as x to the 1 minus p power. Yep, that looks good. Do that integral. Keep the limit sign there. Okay, so we need to do this integral. Keep the p minus 1 there. I need to add 1 to that exponent. I guess that's going to become an x to the 2 minus p instead of 1 minus p, right? Add 1 to 1 minus p, you get 2 minus p. Over that same number, 2 minus p. X going from 1 to b. Oh, let's see. Factor the p minus 1 out. Plug in x equals b. Subtract what you get when you plug in x equals 1. This is pretty similar to what we saw before, but there's a difference. Now we have a power of 2 minus p instead of 1 minus p. This limit is now only going to exist when that power is negative. 2 minus p needs to be negative for this limit to exist. Before it was 1 minus p needing to be negative, and that's equivalent to saying p is bigger than 2, not bigger than 1. If P is bigger than 1, it's a valid PDF, a valid probability density function that can be used to find probabilities. But as far as the mean is concerned, in order for the mean to exist, P needs to be bigger than 2. Huh, what's going on there exactly? If P is between 1 and 2, you can have a probability PDF that follows this distribution, but the mean does not exist. In effect, the mean is infinite. How can the mean be infinite? The mean of data is never infinite, but the mean of a probability distribution can be infinite. What does that mean in terms of real life? Does it mean it's never a valid model for real life? It could be. It could be a valid model for real life when your data every once in a while has very, very high outliers that get arbitrarily large. Yes, they typically cluster close to 1, 1.5, 1.3, 1.8. Every once in a while, you get a million or a billion or a Google. Really? Well, and maybe not in reality, but maybe in a model, it could be reasonably accurate, actually. Ever heard of a black swan event? Right, black swan events are really super rare events, but every once in a while they happen. You might say 9/11 was a black swan event, right? Nobody would ever imagine somebody crashing airplanes into the World Trade Center until somebody did. So in this case, P is bigger than 2, then the limit will exist. And if P is not bigger than 2, it does not exist. And in that case, in this case here, what are you going to get? You're going to get 0 minus 1 over 2 minus P, distribute the P minus 1 through and distribute the minus sign through. You could either write it as 1 minus P over 2 minus P, or you could write it as P minus 1 over P minus 2. Either way, those are the same thing. There's a minus sign there. Let me rewrite it. P minus 1 over P minus 2. You could graph it as a function of P if you like. I've done this kind of thing before. There's how the mean depends on P. And actually, it's got a horizontal asymptote to its graph too. It never gets below 1, no matter how big P is. In any given situation, P would be fixed. But it's interesting to think about what happens to the mean as P varies. I just think that's an interesting thing to think about. All right, well, there's the mean. What about the variance? I guess I'd have to compute the second moment. And remember, the second moment does not equal the variance. Never, ever forget that. Even though once in a while I do. Just a mistake. I'm just so excited to get the second moment that I like all of a sudden think it's the variance, but no, no, no. Maybe you can guess what's going to happen here. Now I multiply the PDF by x squared. I bet P is going to have to be bigger than 3 now for the second moment to exist, and therefore for the variance to exist. I can feel it in my bones. Oops, sorry, P minus 1. The limit as B goes to infinity of, I can bring the P minus 1 out, P minus 1 times this integral, x to the 2 minus P. That'll be the limit, well, okay, factor the P minus 1 out of the limit sign. P minus 1 times the limit as B goes to infinity. Do that integral, I'm going to get x to the 3 minus P over 3 minus P. X going from 1 to B. Yes, very similar kind of calculations. And this limit will only exist if 3 minus P is negative, which is equivalent to saying P is bigger than 3. Then you're going to get P minus 1 times 0 minus 1 over 3 minus P. And that can simplify to 1 minus p over 3 minus p, which is the same as p minus 1 over p minus 3. And you could graph the second moment as a function of p as well, and having a vertical asymptote at 3 and never getting below 1. That's the second moment. That's e of x squared. That's not the variance yet. The variance by the computational formula is the second moment minus the square of the first moment. Oh, that might be a little painful in terms of fractions. I'm not going to do it. You could simplify it. Square that, get a common denominator ultimately of p minus 3 times p minus 2 quantity squared. This is only going to be valid when p is bigger than 3. I'll let you finish it. You finish. And then the standard deviation will be the square root of that. I hope you want to finish it. Okay, have a little fun with some algebra. Maybe even graph it as a function of p. What will its graph look like? I'm guessing shape-wise not too different from that, though it will be a different function. Might go to 0 as p goes to infinity. That's a possibility. Okay, so people do this kind of stuff on the job. They do. Maybe not this particular model, but other similar kinds of models that involve similar kinds of calculations. And the job of the statistician in this context is to say, first of all, is this a good model for some value of p? And if it is a good model for some value of p, what's your best estimate for the value of p? That's the job of a statistician based on data. Not just any old data set, though. It's got to be well gathered data. There are good and bad ways to gather data. You need to use randomness to gather your data as well, to do well-designed experiments, that kind of thing. Not really possible in many business settings, but you have to be, imagine that your sample data is reflective of the wider population is the basic idea. And then your statistical calculations will be valid, and you can maybe estimate a good value of p here. We will come back to this, chapter 7. Maybe we'll come back to this exact same example. We can apply the statistical ideas in chapter 7 and maybe beyond to estimate p.